How are graphs used to solve equations?
Any figure represented by an equation in two variables is a curve in two dimensions. For example, the equation 3x plus 4y equals 8 is also called a linear because the solution represents a line, which is considered a curve in function geometry, on a graph. There are also graphs of equations in three variables, with the solution as a surface or the two-dimensional outer layer of a three-dimensional object.
How does population dynamics use mathematics?
Population dynamics combines observations and mathematics, especially the use of differential equations. For more about differential equations, see mathematical analysis. For example, to determine what the population of a certain country will be in 10 years. Scientists use a mathematical model commonly called the exponential model, or the rate of change of a population as it is proportional to the existing population. For more about population growth mathematics and the environment, see below.
What is mathematical physics?
Mathematical physics uses the concepts of statistical mechanics and quantum field theory. But it is not the same as theoretical physics. Mathematical physics studies physics on a more abstract and meticulous level. Theoretical physics entails less mathematics than mathematical physics and has more to do with experimental physics. But like many fields of science, defining mathematical physics is not easy. For example, still another definition of modern mathematical physics states that it entails all areas of mathematics other than classical mathematical physics.
What were some of the first motor-driven calculating devices?
Many historians believe that the first motor-driven calculating machine was the Intrebari, a device designed by Czechoslovakian inventor Alexander Rechnitzer in 1902. The next step occurred in 1907, when Samuel Jacob Hirsch Stark (1867–1937) produced a motor-driven version of his Thomas-based calculators in Vienna. In 1920 a prolific Spanish inventor named Leonardo Torres Quevedo, 1852–1936, presented an electromechanical machine wired to a typewriter at the Paris Calculating Machine exhibition. His invention performed addition, subtraction, multiplication, and division, and then used typewriters as input/output devices. Interestingly enough, even though the machine made a hit at the exhibition, it was never produced commercially. More and more such calculating devices with electric motors were invented. By the 1940s, the electric motor-driven mechanical calculator had Become a common desktop tool in business, science, and engineering.
What are Napier's bones?
A tool called Napier's bones, also called Napier's rods, was invented by Scottish mathematician John Napier, 1550 to 1617. These were multiplication tables inscribed on strips, also called rods, of bone, not Napier's, but animal bone, ivory, or wood. He published the idea in his book Rhabdologia, which contained a description of the rods that aided in multiplication, division, and the extraction of square roots. For more about Napier, see algebra. Each bone is a multiplication table for a single digit, with the digit appearing at the top of its bone. As seen below, consecutive, non-zero products of this digit are carved in the rod, with each product occupying a single cell. For example, to multiply 63 by 6, the two bones or rods corresponding to 6 and 3 would be put alongside each other and would look like the illustration below. The first number would be the number in the diagonal at the sixth position, 3, then the product, or solution, is evaluated diagonally, or by adding the two numbers diagonal from each other. Or 7, 6 plus 1, and the next number in the separate diagonal, or 8. In other words, 63x6 equals 378. Initially, the tables were used by merchants to speed up calculations. German astronomer and mathematician Wilhelm Schickard, 1592 to 1635, would eventually build the first calculating machine based on Napier's bones in 1623. His device could add, subtract, and, with help, multiply or divide. This is why he is often called the father of the computing era, see below.
In what way do some historians link mathematics to the pyramids?
The pyramids in Egypt were built as royal tombs for the pharaohs, first along the edges of cliffs as low rectangular structures called mastabas, then as tall, four-sided pyramids. The three structures most of us associate with pyramids were built at Giza, near Cairo, about 2500 BCE. The largest of these, the Great Pyramid of the Pharaoh Cheops, measures 481 feet, 147 meters, high. But there are no intricate pathways in this pyramid. It is merely a pile of limestone blocks weighing between 3 and 15 tons.
How is geometry used to create Islamic patterns?
Many of the intricate patterns on Islamic architecture, structures, walkways, and fabric incorporate geometry in the construction of the design. From simple shapes, Islamic designs evolved into complex Geometric shapes involving a high degree of mathematical symmetry. One of the best places to see such work is in the Alhambra Palace, a Moorish structure in Granada, Spain, built in the 15th century. Some Islamic designs were drawn by eye to be aesthetically pleasing. Others involved collaborations between mathematicians and artists. For example, mathematician and astronomer Abu al-Wafa, 940 to 998 CE. Born in today's Iran, worked with artisans in the 10th century, helping to design the ornamental patterns in wood, tile, fabric, and other materials. He discussed such mathematical concepts as constructing a perpendicular at the endpoint of a line segment, constructing a regular polygon, dividing segments into equal parts, and even the bisection of angles. Abu al-Wafa's teachings, and those of others like him, eventually led artisans to design the many intricate patterns seen in Islamic art today.
Why did the need for mathematics arise?
He reasons humans developed mathematics are the same reasons we use math in our own modern lives. People needed to count items, keep track of the seasons, and understand when to plant. Math may even have developed for religious reasons, such as in recording or predicting natural or celestial phenomena. For example, in ancient Egypt, flooding of the Nile River would wash away all landmarks and markers. In order to keep track of people's lands after the floods, a way to measure the earth had to be invented. The Greeks took many of the Egyptian measurement ideas even further, creating mathematical methods such as algebra and trigonometry.
What Greek mathematician made major contributions to geometry?
The Greek mathematician Euclid, c. 325 c. 270 BCE, contributed to the development of arithmetic and the geometric theory of quadratic equations. Although little is known about his life except that he taught in Alexandria, Egypt, his contributions to geometry are well understood. The elementary geometry many of us learn in high school is still largely based on Euclid. His 13 books of geometry and other mathematics, titled Elements, or Stoicheion in Greek, were classics of his day. The first 6 volumes offer explanations of elementary plane geometry, the other books present the theory of numbers, certain problems in arithmetic, on a geometric basis, and solid geometry. He also defines basic terms such as point and line, certain related axioms and postulates, and a number of statements logically deduced from definitions, axioms, and postulates. For more information on axioms and postulates, see Foundations of Mathematics. For more information about Euclid, see Geometry and Trigonometry.
How are some common solids defined?
There are numerous objects defined in solid geometry. The following lists the most common, and some interesting. 1. Cone. A cone can be both a surface and a solid. A solid cone is bounded by a region enclosed in a closed curve on a plane and a surface, formed by segments joining each point of the closed curve to a point that is not in the plane. Note, two solid cones seen with their pointed ends together help define conic sections. For more about conic sections, see elsewhere in this chapter. Pyramid. A pyramid is a polyhedron, see above. With one face a polygon and all other faces as triangles with a common endpoint, vertex. They are named based on the polygon's base, such as the triangular pyramid, square pyramid, and so on. Some of the most famous solid pyramids are the sandstone pyramids of Egypt. These are actually called right square pyramids because the base of the polygon is a square and the vertical line from the vertex meets the center of the base. Cylinder. A cylinder can be both a surface and a solid. A solid cylinder is one that forms by rotating a circle about an axis through the midpoints of the opposite side. It is also called a right circular cylinder. One of the most well-known cylinders is possibly sitting right next to you, a coffee cup. With its cylindrical shape, and the bases, in this case, the base and rim, considered to be congruent circles. Prism. A prism is a polyhedron with two parallel, congruent faces that make up the bases of the shape. The other, lateral faces are considered to be parallelograms. If the lateral faces are rectangles, the prism is called a right prism. Parallelepiped. This strange-sounding polyhedron is one that has all its faces as parallelograms, or a prism with parallelogram bases. The most familiar parallelepiped is a simple box, also called a rectangular parallelepiped that has rectangles for all the 6 faces. For more about these figures, including how to calculate their areas, see elsewhere in this chapter.
How do we interpret dimensions in everyday life?
We are all familiar with dimensions around us, although we may not be aware of them. Most people are familiar with the ideas of two, such as a drawing on paper, and three-dimensional objects, ordinary objects, including an apple or a car, exist in three-dimensional space, but there are others as well. Zero dimension can be thought of as a point in space. One dimension can be visualized by a line or a curve in space. Another way of understanding one dimension is with time. Something we think of as consisting of only now, before, and after. Because the before and after, regardless of whether they are long or short, are actually extensions. Time becomes similar to a line, as in timeline, or a one-dimensional object. Two dimensions are defined by two coordinates in space, such as a rectangle. One of the most obvious two-dimensional objects we see all around us are paintings and photographs, although they represent a three-dimensional object. Even this page you are reading can be considered a two-dimensional object. Though strictly speaking, the thickness of the paper gives it a third dimension. Three dimensions are considered the space we occupy, as three dimensions gives everything around us depth. Our binocular vision allows us to see depth, things in three dimensions. Which is why everything becomes flat or two-dimensional when we view the world through just one eye. One can also conceive of four or more dimensions, but there are few common examples. Most hyperdimensional aspects are used by mathematicians, various scientists, and even economists. They need such dimensional analysis for their complex mathematics, such as for modeling weather patterns or the ups and downs of the stock market.
Who invented catastrophe theory?
Catastrophe theory, or the study of gradually changing forces that lead to so-called catastrophes or abrupt changes, was popularized by French mathematician René Thom. 1923 to 2002, in 1972. Unable to use differential calculus in certain situations, Thom used other mathematical treatments of continuous action to produce a discontinuous result. Although it is not as popular as it once was, it is often used in biological and optical applications.
How are decimal fractions calculated? By adding, subtracting, multiplying and dividing.
Decimal fractions are added, subtracted, multiplied and divided much like whole numbers, but with decimal differences. The following gives some examples. Adding such numbers as 0.3 plus 0.2 is simple. 0.3 plus 0.2 equals 0.5. Adding whole and decimal fractions is also easy. 2.4 plus 5 equals 7.4. These numbers are also easy to subtract, such as 0.3 0.2 equals 0.1. Multiplication and division with fractions is also similar to doing so with regular numbers, although the placement of the decimal point is all important. For example, multiplying 24.45x 0.002 equals 0.0489, dividing the same numbers 24.45 002 equals 12,225. It's interesting to note here a mathematical surprise. In the last example, dividing the small numbers equaled a much larger number, the opposite of what most of us would expect.
Who is Benoit Mandelbrot?
Benoit B. Mandelbrot, 1924, is the Polish-born, French mathematician who invented a branch of mathematics called fractal geometry, which is designed to find order in apparently erratic shapes and processes. a largely self-taught mathematician who did not like pure logical analysis. He was a pioneer of chaos theory, developing and finding applications for fractal geometry. Unlike traditional geometry with its regular shapes and whole number dimensions, fractal geometry uses shapes found in nature with non-integer, or fractal, thus the name, dimensions. For example, twigs, tree branches, river systems, and shorelines can be examined using fractals. Today, fractals are often applied not only to the natural world but also to the chemical industry, computer graphics, and even the stock market.
What is a set?
Simply put, a set is a collection of objects or entities. These are called the elements of the set. The number of elements in a set can be large, small, finite, or infinite. The informal notation used for sets is sometimes seen as x equals y, z, with brackets used to contain the elements within the set. It is stated as, X is a set consisting of the elements y, z, and so on. But more commonly sets are seen as capital letters and elements as lowercase letters. Such as A is an element of set A.
What is perspective?
In painting and photography, perspective gives an image depth, allowing a person to perceive 3 dimensions in a 2-dimensional picture. In art, this can be achieved using certain tools of the trade. For example, the horizon line is the eye level of the artist and viewer. By raising and lowering the viewpoint, it enables the viewer to see more or less of the horizontal plane that lies between the viewer and the horizon. The vanishing point is a point on the horizon line at which parallel lines seem to meet. The classic example is how train tracks seem to come together in the distance. The horizontal baseline is parallel to the horizon line and represents the base of the picture plane. The vanishing point is on the horizon line and is directly opposite, or in front, of the viewer. All of these points, lines, and angles and other ways of bringing depth into a painting are based on concepts in mathematics.
What is mean sea level?
Mean sea level, MSL, is the average water level, height of the sea, for all stages of a tide. Locally, MSL is measured by tidal gauges at one or more points over a given period of time. The resulting numbers average out wind waves and other periodic changes in sea level. The overall values of a MSL are measured with respect to level marks on land called benchmarks. Thus, scientists know a true change in MSL is either from a change in sea level from, for example, possible global warming effects, or changes in the gauge's height on land, such as in the case of local uplift. There is also a more mathematically intensive way to determine the MSL. To a geodesist, a person who studies the shape of the Earth, MSL is determined by comparing measured heights of the global mean sea surface, MSS, above a level reference surface called a geoid, a mathematical model of an ellipsoid shape that approximates Earth's mean sea level. This comparison is done because the Earth does not have a geometrically perfect shape. For example, the Atlantic Ocean north of the Gulf Stream is about 3.3 feet, 1 meter, lower than it is farther south. The MSS is not a level surface, thanks to such factors as currents created by wind, as well as atmospheric cooling and heating that cause differences in sea levels around the world. But interestingly enough, it never differs from the global geoid by more than about 6.56 feet, 2 meters.
What are some statistics used in football?
There are several mathematical statistics used in football. The touchdown percentage is the touchdown passes divided by the pass attempts. The passer, quarterback, rating is determined by 4 elements and their statistical calculations. Percent of completions, average yards gained per attempt. Percentage of touchdown passes, and the percent of interceptions. The average is 1.0, the bottom is 0, and the maximum anyone can receive in any category is 2.375. This is difficult, for a passer to gain 2.375 in completion percents. He would have to complete 77.5% of his passes. Those passers who earn a 2.0 rating or better are exceptional. For example, the National Football League ranks this at 70% in completions, 10% in touchdowns, 1.5% in interceptions, and 11 yards average gain per pass attempt. Rushing is a common statistic commonly heard after any football game on the after-game special. It is the average yards per carry, average, a number measured by the total yards divided by the attempts. In punting, the net punting average, net, is the gross punting yards, minus the return yards, minus 20 yards for every touchback, divided by the total punts.
What are some basketball statistics?
One of the main ways a National Basketball Association coach evaluates a player's game performance is by efficiency, which is determined by using the formula, points and rebounds and assists and steals and blocks. Field goals attempted, field goals made, plus, free throws attempted, free throws made, plus turnovers. Field goal percentage, FG%, is determined by the field goals made. FGM, divided by the field goals attempted, FGA. Finally, the free throw percentage, FT%, is determined by the number of free throws made, FTM, divided by the free throws attempted, FTA.
What are some of the statistics used in baseball?
There are numerous statistics used in baseball, including batting and pitching statistics. Batting statistics can be divided into several numbers. The batting average, is the number of hits a player makes divided by the number of times at bat. It does not include walks or sacrifice hits. The runs batted in, RBI, is the number of runners who scored on a player's hit. Base on balls, or sacrifice. The on-base plus sluggage, OPS, is a good measure of a hitter's ability. This statistic combines getting on base percentage, or OBP, and advancing runners, slugging percentage, or SLG. It is also more accurate thanks to the adjustment 1.2x OBP and SLG, which compensates for the fact that SLG has a wider range than OBP. Pitching statistics include the ERA and WHIP. The earned run average, ERA, is the earned runs times the innings in a game. Most commonly 9, divided by the innings pitched. The walks plus hits per inning pitched, WHIP, records the bases on balls, walks, plus hits divided by innings pitched. It's a good way to measure the approximate number of walks and hits a pitcher allows in each inning that he pitches. It then compares that amount to other pitchers to formulate a pitcher's index.
What is a good example of a topological structure?
Good example of a topological structure is called the Mobius strip, also called the twisted cylinder. It was invented by German mathematician and astronomer August Ferdinand Mobius. 1790 to 1868, in September 1858, although he did not publish his findings until 1865. The strip was also developed independently by German mathematician Johann Benedict Listing, 1808 to 1882, who discovered it in July 1858. Although Listing published his findings in 1861, Mobius's name is used for the strip. This one-sided surface is easy to visualize. Take a long single strip of paper, give one of the two ends a twist. That gives the strip a half twist in its length, or a 180 degrees twist, then attach the two ends. Amazingly, you can verify that it has only one side. It is not possible to paint it with two colors. Even if you cut the strip in half, down the middle, you will still have a one-sided surface. In fact, ants would be able to walk on the Mobius strip's single surface indefinitely, since there is no true edge in the direction of their movement.
What is the value of pi?
Pi is a number, a constant, and to 20 decimal places it is equal to 3.141592653589793233846. But it doesn't end there. Pi is an infinite decimal. In other words, it has an infinite number of numbers to the right of the decimal point. Thus, no one will ever know the end number for pi. Not that mathematicians will stop trying anytime soon. Today's supercomputers continue to work out the value of pi, and to date, researchers have taken the number to more than 200 billion places. For more about pi and computers, see Math in Computing.
What are some other types of analysis?
There are numerous other analyses in mathematics and the sciences besides vector analysis. At one time, the study of tensors was known as the absolute differential calculus. But today it is simply called tensor analysis. Tensors were originally invented as the extensions of vectors. Tensor analysis is concerned with relations or laws that remain valid, regardless of the coordinate system used to specify the quantities. Complex analysis, or complex variable analysis, is the study of complex numbers and their derivatives, mathematical manipulations, and other properties. It is mostly used to find the solution to holomorphic functions, or those that are found in a complex plane, use complex values, and are differentiable as complex functions. Complex variables deal with the calculus of functions of a complex variable, incorporating differential equations and complex numbers. For example, one such variable of the form z equals x plus e, in which x and y are real and the imaginary number I equals -1. Complex variable techniques have a great many uses in applied areas, such as electromagnetics. Functional analysis is concerned with infinite dimensional vector spaces and the mapping between them. It is also considered the study of spaces of functions. Finally, differential geometry is really a branch of geometry, but it includes the concepts of the calculus as applied to curves, surfaces, and other geometric entities. Originally it included the use of coordinate geometry. More recently it has been applied to other areas of geometry, such as projective geometry. In particular, differential geometry uses techniques of differential calculus to determine the geometric properties of manifolds. A topological space that resembles Euclidean space, but is not.
What are multiplication tables?
Multiplication tables are just what the name implies, a table of multiplication. Most of these tables have a specific purpose, mainly to multiply numbers in the rows and columns by each other to find a product. One of the simplest multiplication tables deals with the whole numbers.
What is a linear differential equation?
A linear differential equation is a first-order differential equation that has no multiplications among the dependent variables and their derivatives. Which means the coefficients are functions of independent variables. Other terms associated with such differential equations are nonlinear differential equations, which have multiplications among the dependent variables and their derivatives, and quasi-linear differential equations, in which a nonlinear differential equation has no multiplications among all the dependent variables and their derivatives in the highest derivative term.
What are proofs and theorems in geometry?
Proofs are extremely important to geometry. Similar to other divisions of mathematics, proofs are defined as sequences of justified conclusions used to prove the validity of an if-then statement. For more information about postulates, theorems, and undefined terms, see Foundations of Mathematics. There are essentially 5 steps in showing that any proof is a good proof. State the theorem to be proved, list what information is available. Draw an illustration, if possible, to represent the information, state what is to be proved. Finally, develop a system of deductive reasoning, especially concentrating on statements that are accepted to be true. Along with the true statements, add any necessary undefined terms. In geometry, in order to prove a theorem, you need to use definitions, properties, rules, undefined terms, postulates, and possibly other theorems. And like hyperlinking to other text with internet links. Such theorems can be used throughout geometry, and other mathematics, in the proofs of other new, more difficult theorems.
What are some first-order differential equations?
A first-order differential equation is one involving the unknown function y, its derivative y, and the variable x. As seen above, these types of equations are usually referred to as explicit differential equations. There are several types of first-order differential equations, including separable, Bernoulli, linear, and homogeneous. For explanations of the last two, see below.
What is a one-to-one function?
A one-to-one function is one in which each input, number that replaces the variable, has exactly one output, result of the equation. In such cases, the function needs to pass the horizontal line test, showing that a horizontal line intersects the graph once and only once.
Who was Adam Ries?
Adam Ries, 1492–1559, was the first person to write several books teaching the arithmetic method by the Old Abacus and New Indian methods. His books also presented the basics of addition, subtraction, multiplication, and division. Unlike most books of his time that were written in Latin and only understood by mathematicians, scientists, and engineers, Ries's works were written in his native German and were therefore understood by the general public. The books were also printed, making them more readily available to a wider audience.
How do astronomers determine the distances to the stars?
Relatively nearby objects beyond the solar system appear to shift position relative to more distant objects as the Earth moves from one side of the Sun to the other, a phenomenon called parallax. You can use parallax to determine the distance to stars. As long as these stellar objects are within a few dozen light-years of Earth. More distant objects in the sky do not change their position. Enough as the Earth orbits from one side of the Sun to the other. First, measure the position of the star in the sky, then measure it again in 6 months when the Earth is on the opposite side of its orbit. If the distance A and the angle AC are known, as seen in the diagram below, using trigonometry, C can be determined as A/cos AC.
What are skewness and symmetry?
Skewness is when there is asymmetry in the distribution of the sample data values. In this case, the values on one side of the distribution seem to be further from the middle range than values on the other side. Symmetry essentially means balance, when the data values are distributed in the same way above and below, or on both sides of the middle of the sample.
What is the purpose of the numbers found in a mailing address?
The Zone Improvement Plan, or ZIP, code is a grouping of numbers assigned by the U.S. Postal Service to designate a local area or entity in order to speedily deliver and distribute mail. Zip codes most often refer to a street section, a collection of streets, a structure or building, or a group of post office boxes. But the numbers do not rigidly conform to boundaries of cities, counties, states, and other places. Depending on the area, a zip code includes 5, 7, 9, or 11 digits. In the most common codes 5-digit zip codes, the first digits divide the country into 10 large groups of states numbered from 0 in the northeast to 9 in the far west. Each state is divided into geographic areas identified by the second and third digits of the zip code. For example, New York and Pennsylvania have zip codes starting with numbers between 090 and 199, Indiana, Kentucky, Michigan, and Ohio begin with numbers between 400 and 499. The fourth and fifth digits of a zip code identify the local delivery area.
How do astronomers determine the distances to other planets?
Astronomers need mathematics, of course, to determine the distances to the planets and satellites of our solar system. One of the first astronomers to work this out was Nicolaus Copernicus. See above, using simple observations of planetary positions. One of the earliest methods to determine such distances was to use the orbital period of a planet. This varies as the square root of the cube of the distance from the Sun. T equals kxr, 3/2, in which t is the time for one revolution. R is the distance between the centers of the Sun and the planet, and k is a constant.
What are astronomy and astrophysics?
Astronomy is the study of matter in outer space. It is usually considered a branch of physics. But because it encompasses, literally, an astronomical number of subjects, everything from the study of a star's surface to the end of the universe, it is often considered a field of its own. Astrophysics is a branch of astronomy dealing with the physics of celestial bodies and the universe as a whole. It deals with problems that range from the structure, distribution, evolution, and interaction of stars and galaxies to the orbital mechanics of a near-Earth asteroid.
What is the historical basis for mathematical logic?
Most mathematicians believe that systematic logic began with Aristotle's collection of works titled Organon, Tool, in which he introduced his ideas on logic. In particular, Aristotle used general forms to describe logic, such as if all x are y, and all y are z, then all x are z. He presented three laws basic to all valid thought: the law of identity, or A is A, for example. An acorn will always yield an oak tree and nothing else; the law of contradiction, or A cannot be both A and not A. For example, an honest woman cannot be a thief, and the law of the excluded middle. Or either or, in which A must either be A or not A, for example, a dog can be brown or not brown. Interestingly, author Ayn Rand divided her novel Atlas Shrugged into 3 parts after these 3 principles as a tribute to Aristotle.
Did the Egyptians eventually develop different numerals?
Yes, the Egyptians used another number system called hieratic numerals after the invention of writing on papyrus. This allowed larger numbers to be written in a more compact form. For example, there were separate symbols for 1 through 9, 10, 20, 30, and so on. 100, 200, 300, and so on, and 1000, 2000, 3000, and so on. The only drawback was that the system required memorization of more symbols, many more than for hieroglyphic notation. It took 4 distinct hieratic symbols to represent the number 3577, it took no less than 22 symbols to represent the same number in hieroglyphs, but most of those symbols were redundant. See illustration on p15. Both hieroglyphic and hieratic numerals existed together for close to 2000 years, from the 3rd to the 1st millennium BCE. In general, hieroglyph numerals were used when carved on such objects as stone obelisks, palace and temple walls, and tombs. The hieratic symbols were much faster and easier to scribe, and they were written on papyrus for records, inventories, wills, or for mathematical, astronomical, economic, legal, or even magical works. Even though it is thought that the hieratic symbols were developed from the corresponding hieroglyphs, the shapes of the signs changed considerably. One reason in particular came from the reed brushes used to write hieratic symbols. Writing on papyrus differed greatly from writing using stone carvings. Thus the need to change the symbols to fit the writing devices. And as kingdoms and dynasties changed, the hieratic numerals changed. 2. With users having to memorize the many distinct signs.
What was Pythagoras' importance to mathematics?
Although the Chinese and Mesopotamians had discovered it 1,000 years before, most people credit Greek mathematician and philosopher Pythagoras of Samos, c. 582 c. 507 BCE, with being the first to prove the Pythagorean theorem. This is a famous geometry theorem relating the length of a right-angled triangle's hypotenuse h to the lengths of the other two sides, a and b. In other words, for any right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides.
What is the 15 puzzle?
The 15 puzzle was introduced in 1878 by American amateur mathematician Samuel Lloyd, 1841 to 1911. He called it the Boss puzzle and later the 15 to 16 puzzle. It is one of the most famous puzzles in his book Sam Lloyd's Cyclopedia of 5,000 Puzzles. Tricks and Conundrums, published in 1914 after his death by his son, Sam Lloyd. This puzzle has 16 squares, 15 of them are numbered from 1 to 15 and placed in a 4x4 configuration, with one position, the 16th, left open. The idea was to reposition the squares from a given arbitrary arrangement by sliding them from place to place until they were in numerical order, 1, 2, 3, and so on. For some initial starting points, the rearrangement was possible, for others, it was not. But Lloyd offered a twist to the puzzle. He switched the positions of the squares numbered 14 and 15 and offered $1,000 to anyone who could solve the puzzle. Working out the puzzle became a craze in America, with reports of companies prohibiting employees from playing during office hours. It was as popular as playing computer solitaire is today. Even in Europe, the craze grew. Deputies in Germany's Reichstag played the puzzle. And in France it was claimed to be a greater curse than alcohol or tobacco. But Lloyd knew no one could solve the puzzle, much less remember all the steps taken to try and get to a solution, because there was no solution.
What are geometric transformations?
Geometric transformations are rules that mean there is a one-to-one correspondence between two sets of points in two figures. A geometric transformation changes the plane or three-dimensional space. Each transformation can be defined by thinking about where each point is taken, with the point said to be taken to its image. One way to visualize a transformation is to think of expanding, shrinking, or moving one figure to get a second figure. Depending on the transformation, the image will either be congruent, equal, to the original image, called the identity transformation, similar but not necessarily equal, or will not resemble the original at all.
How are positions on Earth determined?
Positions on Earth are determined using two numbers that represent latitude and longitude. These numbers are actually two angles, measured in degrees. Degree, minutes of arc, and seconds of arc. On a globe of the Earth, latitude lines circle parallel to the equator, and differ in length depending on their location. The longest line is at the equator, latitude 0 degrees, the shortest lines actually pinpoints are at the poles. 90 degrees north at the North Pole, 90 degrees or minus 90 degrees south at the South Pole. In the Northern Hemisphere, latitude degrees increase as you move north away from the equator. In the Southern Hemisphere, latitude degrees increase as you move south away from the equator. Longitude lines, or meridians, once called meridian lines and eventually shortened to meridians, are those that extend from pole to pole, slicing the Earth like segments of an orange, with each meridian crossing the equator. In the Western Hemisphere, longitude increases as you move west from Greenwich, England, 0 to 180 degrees. In the Eastern Hemisphere, longitude also increases as you move east from Greenwich, England, again, 0 to 180 degrees. All points on the same line of longitude experience true noon, and any other hour, at the same time. But note, longitude lines are not to be confused with time zones, most of which follow a more erratic demarcation. For more information on time zones, see below. For more information about latitude and longitude with regard to polar coordinates, see geometry and trigonometry.
What is a point spread?
A point spread is the predicted scoring difference between a game's two opponents. It is used by bookmakers to equalize two teams for betting purposes. For example, if a person chooses the team that is favored, the gambler has to win by more than the point spread in order to get credit for a correct pick. If the underdog team is chosen, the bettor must lose by less than the spread number in order to get credit for a correct pick. If a point spread is listed as off, this means there is no official point spread for the game. For example, if a person picks Army to win, and the team is favored to beat Navy by 5 points, called a spread of 5 points, Army must win the game by 6 or more points in order for the bettor to win. If Army wins by exactly 5 points, the game is called a push, and no one wins.
What is infinitesimal calculus?
Infinitesimal may mean infinitely small in most people's dictionaries, or bring up thoughts of subatomic particles. To those who study arithmetic, however, it may mean numbers greater in absolute value than 0, yet smaller than any positive real number.
Did Einstein's theories change our concept of dimensions?
Yes, our ideas about dimensions changed dramatically thanks to Einstein's theories. Not to mention the mathematics involved in producing those theories. In particular, one can't distinguish space and time as elements in the description of events. Instead, they are joined in what is called the fourth dimension also. Called a four-dimensional manifold known as spacetime, see above. Although it sounds like something out of the television show Star Trek, in space-time events in the universe are described in terms of the four-dimensional continuum. Simply put, each observer locates an event by three space-like coordinates, positions, and one time-like coordinate. The choice of the time-like coordinate in space-time is not unique. Hence, time is not absolute but is relative to the observer. The strange effects go on, in general, events at different locations that are simultaneous for one observer will not be simultaneous for another observer. For more information about dimensions, see geometry and trigonometry.
How is barometric, or air, pressure measured?
Barometric, or air, pressure, named after the instrument used to measure this pressure. is caused by the weight of the atmosphere pressing down on the land, ocean, and air below, with gravity creating the downward force. Because pressure is dependent on the amount of air above a certain point. Pressures are greatest at the surface and less at higher altitudes. On the average, at sea level, the air has a pressure of 14.7 pounds per square inch. A 1-inch square has 14.7 pounds of air pressure on each side. The United States National Weather Service does not measure pressure in pounds per square inch, but in terms of inches of mercury, or how high the pressure pushes mercury in a sealed tube. Air pressure aloft is reported in millibars, or hectopascals HPA. A term most often used by scientists to measure air pressure. Most of us are very familiar with air pressure as it changes with the weather. For example, the use of the terms high-pressure system and low-pressure systems are often indicators of the types of weather fronts traveling through a region. In general, falling air pressure, seen on a barometer, means that clouds and precipitation are more likely. Rising air pressure means that clear weather is more likely. In addition, many people experience personal changes in air pressure. For example, the discomfort, or even pain felt in a person's ears as they ascend or descend in an airplane. A large hill, or even in an elevator, is evidence of changing air pressure.
How does a person determine the odds in horse racing?
The track makes its money in a certain mathematical way, when the odds of the horse race are converted to probabilities. They usually add up to more than 1, giving the track the advantage. For example, say a racetrack has 12 races with 4 horses, and the odds of winning each race are as follows. Note, racetracks don't use the same horse in each race. This example is for illustrative purposes only. Horse 1-1:1, probability equals chances for 1 / total chances 1 + 1 equals 1/2 or 6/12. Horse 2-2:1, 1 / 1 + 2 equals 1/3 or 4/12. Horse 3-3:1, 1 / 1 + 3 equals 1/4 or 3/12. Horse 4-5:1, 1 / 1 + 5 equals 1/6 or 2/12. If a person puts $1 bets on horse number 2, he or she would have to win 4 out of 12 races to break even. But note, all these numbers add up to 15/12, or 1.25, a higher number than 1, so as long as no horse wins more than its probability, the house wins. There's another way of looking at this type of betting. In order for the gambler to do better than the track, he or she has to win 15 times in 12 races, a physical and mathematical impossibility, which is why the track always makes money. Of course, a gambler may bet on certain low probability horses that win more races than expected, earning a few more dollars along the way, but don't bet on it.
What are some of the common metric/SI prefixes?
The common metric and SI prefixes have been around for a while, but some were only recently added. In 1991, in order to apply standard units, SI units, see above, to a wide range of phenomena. Especially in the scientific world, the 19th General Conference on Weights and Measures lengthened the list to accommodate larger and smaller metric numbers, with the list now reaching from Yate to Yocto dash.
How did applied mathematics grow over time?
Historically speaking, applied mathematics was always concerned with using mathematics to solve problems in physics, chemistry, medicine, engineering, the physical sciences, technology, and biology. In fact, applied mathematics is older than pure mathematics, as it was used in areas that formed the core of early physics research, such as mechanics, fluid dynamics, and optics. As mathematical tools became more powerful, these areas of physics became more mathematically based. This mathematical analysis tie to science and engineering has always had a great place in history and has led to some of its greatest discoveries.
How can functions be defined based on variables?
A function having a single variable is said to be univariate. With two variables, it is bivariate, and with more than two variables it is multivariate. Although two variables are considered multivariate by some people.
What are the humanities?
Humanities are those studies dealing with the fine arts, painting, drawing, and so on, literature, philosophy, and cultural science. This field focuses on the idea of expanding human thought, intellectual skills, and accomplishment through the study of these branches. Although the humanities seem far removed from mathematics, there are actually many connections.
What are time zones?
Time zones are any of the 24 regions on the globe, loosely divided by longitude but more erratic in their demarcations, which is divided according to the number of hours in a day. Within each zone, all clocks are set to the same time. Time zones include the international date line, an imaginary line of longitude generally 180 degrees east or west of the prime meridian. The date becomes 1 day earlier to the east of this line. Time zones are truly a product of mathematics. Initially, people used local solar time, resulting in slightly different times between towns. With technology, especially trains and telecommunications, more accurate timekeeping became a necessity. Thus, time zones helped solve many of the problems by Setting the clocks of a region to the same mean solar time. The time zones made it easy for neighboring time zones to be labeled 1 hour apart. Not that the system is perfect. The hour separation is not universal. And because they often follow political boundaries, the shapes of the time zones can be extremely irregular.
What are the rules for combining logarithms?
There are certain rules for combining logarithms. In the following cases, let a be a positive number that does not equal 0, n is a real number, and u and v are positive real numbers. Logarithmic rule 1, loga, uv, equals loga, u, plus loga, v. Logarithmic rule 2, loga, u/v, equals loga, u, loga, v. And logarithmic rule 3, loga, u, equals n loga, u. This can be expressed as follows, in rule 1. Multiplication inside the log is turned into addition outside the log, and vice versa, in rule 2. Division inside the log is turned into subtraction outside the log, and vice versa, and in rule 3. An exponent on anything inside the log can be moved to the front of the log as a multiplier, and vice versa. But remember, these rules only apply if the bases are the same. For example, because the bases are not the same in loga, u, plus log, v, this expression can't be simplified.